Alright, in this video and also the next video, we are going to study the geometry of complex numbers. As we have seen before, a complex number such as this, a plus ib, where a and b are real numbers, they correspond to the point ab in the two-dimensional space. As such, we can plot each complex number on the two-dimensional Cartesian space, Euclidean space, such as this. So if there's a point AB where the x coordinate is A and the y coordinate is B, then this can represent the complex number, such as A plus IB. So this has many interesting implications, which we are going to study now. So let's start. Okay, first we define the absolute value or modulus of a complex number. Let's say complex number z is equal to a plus ib, and a and b are of course reals. Then its absolute value denoted as this, just like the absolute value of a real number, is defined as the square root of a squared plus b squared. Of course, what this means is the distance between the origin on the plane and the point. So this is, okay, so if this is z, then this distance means the absolute value of the complex number. Now, let's compare this absolute value with the absolute value of a real number. If you remember, let's say if x is a real number, then the absolute value of x is defined as equal to x if x is positive or 0, or negative x if otherwise, that is, when x is negative. Okay, but the same thing can be written also as square root of x squared, right? Because x squared and negative x squared, they are both x squared. And so if you take the positive square root of that, we get the absolute value of x. And actually, this definition of the absolute value of a complex number is a generalization of this definition of the absolute value of a real number. Because if this complex number is purely real, that is when b is 0, then when b is 0, then this is just a square root of a squared. That is, it's the same as this one. And also in terms of geometric property, so any real number can be plotted on a line. So it's a number line, let's say from 0 to something. And if the value of a is somewhere here, then the absolute value means the distance between the origin and this point, right? So this is a, the absolute value of a real number a. When a is negative, when a happens to be negative, let's say a prime is negative, then the absolute value of a prime is the distance between that point and the origin, right? So when this is negative, then this is equal to negative a prime. Yes. If a is positive, then this is equal to positive a. So in both cases, the absolute value means the distance from the origin, okay, either in reals or in complex numbers. Okay. Oh, by the way, maybe I forgot to mention that this plane, when we regard this plane as a set of complex numbers, this plane usually called complex plane. Complex plane. Or some people prefer to call it an Argand diagram. Argand diagram. Same thing. And next, let's define complex conjugate. So suppose we have a complex number z equals to a plus ib, then its complex conjugate of z is written as z bar, and that is defined as a minus ib. So we just swap the sign of the imaginary part. So what does this mean? So if we have, let's draw on the complex plane. Suppose we have a plus ib here. Okay, then the complex conjugate. So z is this. The complex conjugate of this number is this one. So the coordinate is a and minus b. So that means we take the mirror image around the x-axis, the horizontal axis. So that is, so minus b, and this is b, and this is a. So this corresponds to a minus ib, which is the complex conjugate of z. And here's a nice property about complex number and its conjugate. And if we multiply them, so z with its conjugate, then what we have is this. So if z is a plus ib, then z bar is a minus ib. So if you calculate this, this becomes, so this, this is a plus ib, and this is a minus ib. So what we get is a squared minus ib squared. And of course, I squared is negative 1, so we have a squared plus b squared. So what is this? Remember, this is the square of the absolute value of z. So the complex conjugates and the absolute value are related in this way. Okay, now let's see a bunch of properties of complex numbers and complex conjugates and the absolute value of complex numbers. So here is a lemma. There are actually 9 properties I'm going to show. So that is, for any complex number z, we have its complex conjugate of its complex conjugate. The complex conjugate of z is equal to z itself. And for any two complex numbers, say z1 and z2, we have the complex conjugate of their sum is the sum of their complex conjugates. Okay. And 3. If z, the complex conjugate of z is equal to z itself, then that means the number z is actually real. So the imaginary part is 0. And 4. If the complex conjugate of a complex number is equal to negative of that complex number, then that means this number z is purely imaginary. Okay, and let's see, and 5. For any complex number z, z plus its conjugate is always real. Okay, so I think this is easy to see. And 6, for any complex number z, the difference between z and its conjugate is purely imaginary. So real part is gone. And 7, for any two complex numbers, z1 and z2, let's see, we have the complex conjugate of their product is the product of their complex conjugates. And 8, for any two complex numbers, the absolute value of their product is equal to the product of their absolute values. Okay. And finally, for any two complex numbers, complex numbers, we have this triangle inequality, that is the absolute value of their sum, z1 plus z2, their absolute value is less than or equal to the sum of their absolute values. Okay. And this last inequality appears in many places in mathematics, and it's called the triangle inequality. Okay, why it's called triangle will become apparent later in the proof. Okay, so let's prove this. And first, let Z be A plus IB. Of course, A and B are reals. Then its complex conjugate is, by definition, A minus IB. So the complex conjugate of this is A minus I minus B, which is A plus IB. Right? Minus and minus will cancel. So this is equal to the original Z. So it's done. And second, let's say Z1 is A1 plus IB1 and Z2 is A2 plus IB2. So their sum is, if we add real part and real part and imaginary part and imaginary part, we have A1 plus A2 plus B1 plus B2. So the complex conjugate of this is A1 plus A2 minus B1 plus B2. But if we split these sums, then we can write the same thing as A1 minus IB1 and plus A2 minus IB2. But this is the complex conjugate. A1 complex conjugate of A1 plus BI1 and A2 plus IB2. So we have the sum of the complex conjugates. And we are done for this one. And for the next one, what was it? 3. Actually, this is, if this is true, then Z is real, but also the converse is true. And the same for this one. So suppose, let's say Z is again A plus IB. Suppose Z is equal to its complex conjugate. Then that means A plus IB is equal to A minus IB. Okay, so that means this A is cancelled, so IB is equal to negative IB. So 2IB is equal to 0. So that means B is equal to 0. Okay, we don't care what the value of A is, but surely B is equal to 0. Therefore, that means Z is actually equal to A. So it's real. Okay. So if this holds, then this holds. z is real. What about the converse? Suppose z is real. Then z is so then the imaginary part is 0. So z is something like a plus I 0, right? Imaginary part is 0 because it's real. Therefore, z conjugate is also a. Okay? Therefore, which is equal to z itself. So the converse is also true. And we are done. And in a similar manner, you can prove that if z is equal to its negative of its conjugate, then z is purely imaginary. And vice versa. You should try that. And next, z plus z conjugate is, let's say if z is a plus ib, then its conjugate is a minus ib. So these are cancelled. So we have 2a, which is purely real. And similarly, you can prove that this is purely imaginary. Okay, so this was 5 and this was 6. So the next one, 7, is z1, z2 conjugate. So the conjugate of a product is the product of conjugates. Okay, now let's prove this one. So again, suppose z1 is equal to a1 plus ib1 and z2 is a2 plus ib2. And so let's consider the conjugate of the product, and this becomes conjugate of a1 a2 minus b1 b2. So this is the real part, and let's see, a1 b2 plus b1 a2. So the conjugate of this is negative sign here. Okay, now next, so the left hand side is this, the right hand side times z2. The right hand side is a1 minus ib1 times a2 minus ib2. So this is a1 a2, and this becomes minus b1 b2. And we have negative signs here, so this becomes a1 b2 plus b1 a2. So they are equal. See, this is equal to this, therefore this is true. Okay, next, 8 is the absolute value or the modulus of a product is the product of the absolute values. You can show this by direct calculation, but there's an easier way using, remember this relation. So the product between a complex number and its conjugate is the square of the absolute value. Okay, let's use this one. So that means if we square this, z1, z2 squared should be equal to this complex number, the product, times its conjugate. Right? However, we know that the multiplication or between complex numbers is associative and commutative. So we can just switch the order of these components. So this is equal to z1 times z1. By the way, this is equal to So the complex conjugate of a product is same as the product of complex conjugates. So we can split this and we can switch the order. So Z1 times Z1 bar and Z2 times Z2 bar. But this one is equal to the absolute value squared of Z1 and same for Z2 squared. So now we have this equal to this and take the square root of both sides, and the absolute value is always non-negative. Therefore, we have this. Okay, we don't need plus minus sign here because both sides should be non-negative. So this is it. Okay, finally, let's prove the triangle inequality. So Z1 plus Z2, its absolute value is less than or equal to the sum of the absolute values. Okay, what this means is this. On the complex plane, so this is real axis and this is imaginary axis. If we have 2 points, Z1 and Z2, say, so we can draw this diagram. So if we add these two numbers, the result is something like this. So we translate, let's say, Z2 along the direction of Z1. So if we move this, then move this to this side, then we have this. Okay, so the length of this is Z2 absolute value. So this is Z2 absolute value. So here we have a parallelogram, and this length is the same as this length, and this length is same as this length. Okay, so as a result, we have a new complex number here. This one actually represents Z1 and Z2. And we will study this in detail in a later video. But anyway, for now, just believe me. Okay? So we have this triangle. This, this, this. Okay. Of course, this length is the absolute value of Z1. Okay? And this length, okay, the length of this edge is the absolute value of Z1 plus Z2. So what this inequality shows is that the sum of the length of this edge and this edge is greater than the length of the remaining edge. So this holds for any triangle. Therefore, it's called the triangle inequality. Anyway, let's prove it. But of course, as soon as we understand the sum represents this edge, then the proof is almost obvious from this figure. But anyway, let's prove that algebraically. Okay, so first of all, suppose we have a complex number alpha. So as we have seen before, alpha minus alpha conjugate is purely imaginary. So the real part is gone and only the imaginary part remains. So therefore, if we square it, remember, be careful, this is just square of this one. It's not absolute value squared. So this is negative, or maybe 0, in case it's 0. Okay. So now, to both sides, we add this. So 4 times alpha alpha bar, which is actually equal to 4 times alpha absolute value squared. So add this to both sides of this. Okay. Then we have alpha minus alpha bar squared plus 4 alpha alpha bar less than or equal to 4 alpha absolute value squared. Okay. Now, this left-hand side, if you expand this and add this, we have alpha squared plus 2 alpha alpha bar plus alpha bar squared, which is alpha plus alpha bar squared. So this is less than this thing. Okay. Okay, now take the square root of both sides. Then we have alpha plus alpha bar less than or equal to 2 times alpha modulus. And actually we have this side also negative 2 alpha modulus, but this time it's not necessary. So anyway, this inequality holds for any complex number alpha. Remember, alpha plus alpha bar is always real, so this does make sense. So let's say alpha is a product of z1 and z2 bar. Then substitute this into here. We have z1, z2 bar plus z1. So the complex conjugate of this is z1 bar times z2 less than or equal to z1, z2 bar. Okay. And the right-hand side is, of course, equal to 2 times z1 absolute value times z2 absolute z bar absolute value. But the absolute value of z bar is equal to the absolute value of z. So we can just get rid of this bar conjugate. Okay, now we have this equality. So z1 times z1 bar is equal to z1 absolute value squared, and z2 times z2 bar is equal to z2 absolute value squared. So add this to both sides. Then we have this plus this plus this plus this. So z1, z1 bar, and z2, z2 bar, and z1, z2 bar, and z1 bar times z2 is less than or equal to this thing. So z1 bar, z1 absolute value squared plus this and plus this. Okay, now we can factorize the left-hand side. So z1 is here, z1 is here. So z1, z1 bar plus z2 bar. And let's see, z2 is here, and z2 is here. So z2 and z1 bar plus z2 bar. And this one can be factorized as, of course, z1 plus z2, both absolute values, everything squared. And this can be further factorized as z1 plus z2, z1 bar, and z2 bar. And this is z1 plus z2, and this is z1 bar plus z2 bar, so that is actually z1 plus z2 bar. So this is equal to z1 plus z2 absolute value squared, which is less than or equal to this thing. So z1 absolute value and z2 absolute value, everything squared. So if we take the square root of both sides, we finally get this. Of course, since the absolute values are always non-negative, we can just take the positive side of the square roots. Now we're done. Now let's go back to the initial argument of a complex plane. So we have real axis, imaginary axis, any point z equal to a plus ib. This real axis coordinate is a, and the imaginary coordinate is b, and the absolute value of this complex number is the distance from the origin, right? Another important quantity to express the point in complex plane is the angle from the real axis, okay? And that angle is called the argument of the complex number, and we write arg of z. So this represents the angle between the real axis and this line of the complex number, okay? And of course, this angle is not unique, because if we continue rotating 2 pi, then we still have the same angle. We can represent still the same point by theta plus 2 pi. Okay, 2 pi, or for that matter, theta plus 2 pi times any integer k can represent the same point. Okay, so it's not unique. But anyway, every point on the complex plane can be represented by either real part and imaginary part, or the length, the distance from the origin, and the argument. So once we determine the distance from the origin and the angle from the real axis, then we can uniquely determine a point in the complex plane. So anyway, let's define the argument a little bit more formally. First, we define the argument of a complex number where the absolute value is 1. Okay? If the distance from the origin is 1, then that point resides on the unit circle centered at the origin, right? So real axis and imaginary axis, and the circle with radius of 1. So that's distance of 1. Okay? So this angle means the length of this arc from the real axis. Okay, that's the definition of the angle. Okay, this length corresponds to the angle from the real axis. Okay, that's called the argument. And as I said before, it's not unique, because if we rotate by 2 pi or any integer multiple of 2 pi, we still have the same point on the unit circle. So the argument is not unique. So argument is of a complex number with length 1 is not unique. So it's actually a set of some angles plus 2 pi times some integers, all integers. So they all represent the same point in the unit circle. And particularly if the argument in the interval between negative pi, not inclusive, and positive pi, inclusive, is called the principal argument. Principal argument. And we write with capital A, arg of u. So this is a real number. It's not a set. So this is a set, but this one is a real number. So in this case, it's theta. Okay. For the general complex number that does not reside on the unit circle, then for any non-zero complex number, we can write this as the absolute value of z times z over absolute value of z. And this one is on the unit circle because the absolute value of this one is, of course, the absolute value over the absolute value, which is 1. So this does reside on the unit circle, and for that complex number, we can define the argument. So that argument is defined to be the argument of this complex number. Okay. So for any complex number, the angle from the real axis is the argument. So for example, arg of 1, of course 1 is a complex number which happens to be real, is 0 because its angle from the real axis is 0 degree. So this is principal argument, and general argument here is 0 and 2 pi, plus minus 2 pi, and plus minus 2 times, let's say, 2 is 4 pi, and so on. So there are infinitely many angles. And argument of I, the imaginary unit, is pi half. And on the complex plane, this I resides somewhere here. And it is on the unit circle. And the general argument is this plus minus multiple of 2 pi's, and so on. And you should try to find the argument of -1 or argument of negative I, or argument of whatever the complex number you want to deal with, something like this. Try to find them. Okay, that's all for this video. See you later.